My name is Wolfgang Bernhart. I'm a senior partner at Roland Berger. We are a strategy consulting company. I'm based in Stuttgart, but I run our what we call Advanced Technology Center, and a significant part of that is our battery team. And within that battery team, with that battery team, together with my colleagues in the industry verticals, we provide consulting services to our clients. We have done probably 200 projects, roughly 200 projects along the battery value chain, whether it's with automotive OEMs, ESS players, on cell manufacturing, with material companies, with recycling companies, with a global team of roughly 50 technology and market experts, with hubs in North America, in Europe, and Asia. And that's mainly focused on investor support, like commercial and technical due diligence, red flag assessments, other financial advisory, but also strategic advisory, growth strategies, product market entry, etc., as well as topics around the value chain, participation models, partnering strategies, and operational support in terms of product cost reduction, gigafactory planning and execution support, footprint and site selection. So what I'm going to talk today, as already mentioned, I will talk about all solid state batteries and how we see the role and the status of those batteries that have the potential to further push the energy density versus conventional lithium-ion batteries up to 1,000 watt-hours per liter. So what's currently in production, as you know, is the ternary chemistries, NMC, NCA, LFP, mid-nickel chemistries that gain increasingly more traction, as we see again, because of the broad availability and the still relatively low cost despite the higher raw material shares. And we do see sodium-ion batteries being developed, but relevant in terms of automotive only for the entry segment. Could get more traction on the stationary side because of their safety features and the possibility to transport them, for example, completely discharged, but only if lithium prices are above $20 per kilogram LCE equivalent, because below that they are actually not competitive with LFP batteries. We do see LMFP and NMC blends, as well as pure LMFP for the medium and premium segment, and relevant for entry and medium segment LMFP, pure LMFP cells that are already produced in China and used in China and are by some Western OEMs also being explored and potentially being used. Then there's manganese-rich as a different type of ternary chemistry being developed by Western, specifically by Western cathode material suppliers. And then the solid-state technology that actually mainly differs on the anode side, that can get a much higher energy density and potentially also benefits on the safety side, but is still not really in production, despite some polymer-based solid-state batteries with lithium metal foils that are, for example, being produced by Blue Solutions in France and have been used or are being used in buses, for example, at the Paris Olympic events. However, the current generation is, from a performance perspective, not sufficient yet for general automotive use. The operating temperature range is too high. Actually, it works mainly in an operating temperature of 80 degrees Celsius, but there are no new developments ongoing in order to run those at ambient temperature. There are other approaches. They still struggle, but we already see at the same time promising developments, and I come to that a little bit later when comparing what we see from the different companies. So if we compare all solid state batteries, we need to look at the volumetric and the gravimetric energy density. And as you can see here with the dotted lines, all solid state is better than what we have today with NMC, even with NMC with graphite and for example 5% silicium. But the issue is it's also not necessarily much better than nickel-rich chemistries with a silicium-dominant anode, so and potentially a liquid electrolyte. So what we see is that lithium-ion cells with nickel-rich cathode active material can already achieve a relatively high energy density in terms of volumetric energy density. And those systems where the anodes contain engineered silicon particles already allow promising increases of energy density. Just a few examples by Amprus, for example, they claim to reach up to 1200 watt-hours per liter. And we do see high gravimetric energy density as well, fully compatible with liquid electrolytes. But all solid-state batteries show the potential to significantly improve both the volumetric and the gravimetric energy density due to omission actually of anode active material. So if we compare, and this is obviously a very high-level comparison that needs to be done for specific chemistry, but as an overview, if you compare all solid state with silicon dominant lithium-ion batteries, the energy density can get higher. What's often an issue is the C rate. Lots of companies are working on the topic to get a higher fast charging capability, but actually due to the lower ionic conductivity, this is an issue. While with silicon dominant designs, depending again on the specific chemistry and how it's being done, there are faster charging or higher fast charging rates possible, 4 C or even up to 10 C. From a safety side, there's an intrinsic safety to the stable electrolyte claimed, but that has to be proven for lithium metal anodes on the anode side that really provide the additional energy density. For silicon dominant designs, there's not a big difference. It's to cell safety that's majorly influenced by the cathode. Lifespan cycle life is an issue. We don't have the cycle lives that we can achieve with specific designs with LFP batteries, for example, that are designed for stationary usage. So that's an issue that has to be tackled. However, there are, as we see, first designs that should go in the right directions and achieve the at least 800 to 1,000 cycles that are needed for automotive applications. On the silicon dominant side, the swelling and gassing is the biggest issue, and that is something that needs to be solved. Again, something that has to be done. On the production side, we do see very different types of designs. If you look, for example, the polymer-based approaches, they have I would say, significantly less complex production process. So while the production looks slightly different, it can be potentially cheaper in terms of equipment. But it doesn't use in that case the already built up factories. While silicon dominant designs often are drop-in solutions, so actually what changes is only the anode material. On the thermal management side, there are additional requirements, or can be additional requirements due to higher operating temperature, for example, preconditioning. If we talk about those, if we talk about those polymer-based solid-state batteries, while we don't have any additional thermal management requirements with silicon based designs. So how does it look like from the left to the right? If you look at a conventional lithium-ion battery, you typically have a current collector, a copper foil. Then you have the anode active material, AAM. You have the cathode active material, in between a porous separator, and typically a liquid electrolyte that's being done. So the entire cell is filled up with this liquid electrolyte, and that's the basis for the energy density. Then a second topic that's being typically explored together with other approaches is a graphite or a silicon anode, or a high silicon anode. So again, you have the current collector, you have on both sides, you have the cathode and anode active material, and you have a solid state electrolyte that could be a separator electrolyte based either on polymer, on sulfide, or on oxide. All those have different properties and different effects. The energy density compared to conventional lithium-ion batteries, with graphite it could be lower, but with silicon it can be higher. And then you have the ASSB with lithium anodes, actually as either full solid state or as semi-solid state. So you typically have a lithium foil that can be either a freestanding lithium foil, it can be a lithium that is deposited on a current collector, but metallic lithium, or you have a current collector and actually a lithium as being deposited during the first charging cycle, often or sometimes also referred to as anode-free design. So the anode material, the graphite anode material, is replaced by lithium foil, and that's the standard design, I would say, for most of the all solid state approaches. Some of them, or most of them, use also catholyte. Not all of them. Some are able to avoid that, specifically if they use polymer. Then the polymer is actually penetrating through the cathode material as well, and you don't have any catholyte as well. You also have sometimes protective layers on the solid state electrolyte in order to prevent the dendrite formation. That is also the main issue. So with conventional liquid electrolytes, during the charging process, lithium ions are deposited unevenly on the cathode and can form microscopic dendrites. And if those dendrites build up and penetrate the separator, you have a short circuit or a thermal runaway, and you have all these events that you don't want. So having a lithium metal anode with a conventional electrolyte can lead, or will lead, almost certainly lead to dendrite formation that grow through, and that means you have a short cycle life, you have reduced battery efficiency, and you have the risk of short circuits, which may cause fires or explosions. So you use that solid state electrolyte to block the dendrite formation, and the suppressed dendrite growth enables the use of the lithium metal anode, and that again, that allows to increase significantly the energy density. So we expect in the next couple of years that graphite and silicon-based anodes still dominate by the end of the decade, and lithium metal anodes for all solid-state batteries are still somehow in the niche. So somewhere between 1% and 2% might be an appropriate figure. That would mean we may have between 60 to 100, maybe a little bit more, gigawatt hours in production capacity for all solid state batteries. Obviously, that is still a kind of looking in the glass bowl. But what we see from around the globe, and even with the now announced increased efforts of the Chinese, for example, it will take some time. It will take some time to get it up in size, to produce really not single layer coin cells, but large automotive cells with more than 100 layers, etc. So the key growth is in silicium chemistry that can have up to tenfold energy density versus pure graphite. That's a common and inexpensive material, and we do see that there's a lot being done. But lithium metal gets also traction quite rapidly. Now, who are the players? And that is not exhaustive, but I think we captured quite a lot. We do have in the West, starting maybe in the US, we have the well-known companies like QuantumScape that use oxide electrolytes and lithium-free anodes. We have Solid Power with sulfide electrolytes and lithium and silicon anodes. We have SESAI with semi-solid electrolyte, Factorial with polymer electrolyte and lithium metal anode. And then in Europe, actually two players, on one hand, Bolloré and Blue Solutions. I already mentioned them. They are already on the road with their third generation technology and planning for fourth generation that should work in ambient temperature based on actually a polymer electrolyte and a lithium metal anode. And you have Basqualt in Spain that also works with polymer electrolytes, but would rather go for graphite anodes. At least that's my understanding, and in order to keep costs down. In Asia, we have in Korea's Samsung with sulfide electrolytes and lithium-free anodes in a very in a very advanced development status, but still the big challenge here are the costs. And we have a couple of companies in China. There's CATL. They used to work on something that's not really solid state, a condensed battery, but they are working now also on solid state batteries together with a couple of other companies pushed by the Chinese government, and I will come to that a little bit later. We have Prologium in Taiwan with an oxide electrolyte and a silicon oxide anode. They are in the process of planning and building a gigafactory in Europe, in the north of France. We have Neon V Lion with a semi-solid battery. They are already in CS production, but with an energy density that is not higher than what we see with conventional batteries. We have Dongfeng and Gangfeng. They already started a prototype car with a solid state battery, but from that prototype to CS production, it's quite some time. And we have Qingdao and SAIC. Now looking a little bit deeper in the performance, again as an overview, and the maturity levels, everybody's trying to get from the left to the right. So that was already a couple of quarters or at the beginning of the year. So they moved up the ladder. Most of these companies being in a little bit more advanced development stage with different type of performance. The ones that are already in production with relatively low energy density, again comparing with advanced high nickel-rich conventional lithium-ion batteries, we can achieve 600, 700, 800 watt-hours per liter. So not really better. The better ones are still to come. What is that? And again, that might not be the latest data. Development is ongoing. The companies develop further, so it's partly a couple of months old, the data. But what you can see is a big spread between the different companies. We Again, also factorial, for example, I think they are now in a sample stage, but in any case, what they are working on is to increase the temperature range and the charging and discharging power. That is, as you can see, across the different companies, a bigger issue for those that want to achieve higher energy density. The other topic is the operating temperature. In fact, you should achieve something that is at least ambient temperature, better below that, or minus grades. If you think about vehicles that are being used in countries or in regions where in the winter you have minus degrees or below 0 degrees Celsius, then you have to have an operating temperature that allows a cold cranking, a cold start capability, and that is still an issue. Cycle life is another one. So nobody is really mastering from our perspective at that time, all the necessary KPIs, but everybody's working on that, but it will take time to really get that to mass production with a yield rate and with yield rates that are acceptable and that allow for production that is economically feasible. If you look at China, then they started to push forward with the so-called China All-Solid-State Battery Collaborative Innovation Platform that has been established in January this year. It's being pushed by the government, by the central government and certain regional government. Major players have been urged to participate, so they got a recommendation to participate in that platform, and they are all working on that together with some well-known automotive OEMs and industry associations and large universities. The goal is basically to compete with Toyota, that has the most patents in all solid-state batteries, while all these companies have less than 100 patents, which is close to nothing if you compare, for example, the 20,000 patents that CATL has in total. It's to overtake US-located ASSP startups like Solid Power, QuantumScape, etc., or Factorial, to build a complete battery supply chain by 2030, including the fundamental research, but also the materials, the supply of lithium metal foils. And they announced an investment to advance that over the next couple of years. They typically plan to produce ASSP featuring sulfide-based solid electrolytes and silicon anodes, with a target of 400 watt-hours per kilogram and 800 watt-hours per liter at the cell level between 2027 and 2030. And then in the second step, to go to sulfide-based solid electrolytes with lithium metal anodes and increasing again the energy density. So where are we here? There are certain cell producers that are in. There's one that is already in pilot line. As I said, it's more from an energy density perspective. According to the plan, they plan to go SOP in around 2027 with a sulfide electrolyte and a silicium anode with 30 to 50% silicon. There's a second one already still in lab scale. They want to go for pilot in 27, so probably not in SOP before 2030. Slightly higher energy density with a semi-solid electrolyte, but interestingly enough, also looking at sodium ion combined with solid state technologies. And then there's a third one. That's not really clear what the cell chemistry is. We were not able to get that. We have various OEMs. Again, they plan to come to the market with demo cars mainly. But as you can see here, even that is for the time being mostly in the demo stage, and the only one that's coming to the market is actually a solid state polymer separator with a ceramic layer and a liquid electrolyte, and then a sulfide electrolyte in a second step. They didn't mention the energy density. I think it's not that much higher than what we do see currently. So having said that, to summarize and give us hopefully a few minutes for Q&A, we do see all solid-state batteries that they have the potential to further push energy density versus conventional lithium-ion batteries up to 4,000 watt-hours per liter and 400 or more watt-hours per kilogram. There are various approaches, but the full potential can only be achieved by lithium-free or lithium metal anodes. So by getting rid of the cathode material that consumes a lot of space. We do see multiple disadvantages and technology hurdles still, mainly around the C-rate, the industrialization challenges. For example, when you talk about oxide separators, to really get them with the right yield rate and with no defects. If you have, for example, 99% yield in, or if you only or if you miss 0.1% of defective separators in a layer, in a single in one single layer cell, that would mean if you scale that up with that yield rate to large automotive batteries with 100 or more layers, you add a yield of 20-30%, which is completely unacceptable. So you have to have a very, very stable production process for these, specifically for these real solid separators. China is catching up, as we know, and it has been mentioned before. CATL is now deploying 1,000 people on the Silicon State side. That needs to be monitored closely. The amount of money going in R&D is tremendous. As it has been published by CATL, for example, last year they spent $2.6 billion in R&D, and they have meanwhile more than 20,000 people in the headquarters working on advanced technologies. That's quite a lot. So various OEM partners typically work with more than one player to keep all the options open. Corporations are not exclusive, are open for third parties. The different players strongly differ regarding performance and maturity. From our perspective, there's no clear winner yet, and the market should be closely and continuously monitored and regularly assessed to established best-in-class cell manufacturers in order not to miss anything out here on that side. With that, I'm at the end of my presentation, and I hope we have some time to answer questions or discuss.
Excellent job, Wolfgang. I do have a question. Could you briefly describe what the failure mode is of solid-state battery chemistries?
Yeah, I think it's one of the areas is still dendrites formation. That this doesn't work out, and then to be honest, I'm not that deep in that failure modes. It's more on the production side. On the production side, I would say it's a scale up, and it's it's really the way to the industrialization. Yeah, also industrialization of the metal foils and get them down to below 18 microns. Which is needed in all freestanding lithium metal foils, which is needed in order to really achieve a higher energy density is still a challenge at reasonable costs.
Is that like maturation or the industrialization of the process what gives the batteries lower cycle life?
Excuse me?
You were mentioning in the presentation how solid state batteries are expected to see maybe 500 to 1,000 cycles
Yeah.
for usable life. Is that just because, like you said, the manufacturing isn't matured yet? Is that what causes a lower cycle life?
Yeah, it's one of those topics. It's also the yeah, I would say that's one of the issues, yes, most likely.
Okay, thank you.
Do you think
Yeah.
that introduction of semi-solid electrolytes actually defeats the purpose because there are more possibility of dendrites growing in a semi-solid environment? For example, you can drive discharge into reversal cell, and then dendrite would appear from the side you wouldn't expect them to appear.
Yeah,
So
but I mean, I think that has been shown already in that this works, but not with the performance that one would expect from a solid state battery. But if you look at these polymer batteries from Bolloré Blue Solutions, they are actually being used for 8-9 years now. We had the whole so-called blue car series, that was a car that did run. It's not in operations anymore, but it did run for 7 years in Paris as a mobility solution, and that used actually that polymer technology. So a lithium metal foil already for quite some time, and then the polymer technology and a polymer-based electrolyte and a dry extruded cathode material. They had one incident, a fire, but that was actually related more to the design of the pack that is more or less you could even call it electrode to pack technology, and they had a short circuit that was not really related to the design of or to the cell chemistry, but to a production failure in the pack. Yeah.
is it
So-
an old technology which is 3M hydroquebec, really? What Blue
Sorry?
Solutions? Is it an old technology 3M hydroquebec? What they use, Blue Solutions?
To be honest, that I don't know, but whether that is from Hydro-Quebec or not,
Mhm. Yeah, it's 80s.
yeah, it can be. Yeah.
Was developed in 80s, but that's fine.
Okay, as far as the lithium metal anode is concerned, which you just mentioned, having lithium metal anodes as thin as 18 microns or 16 microns or even lower. My name is Bernhard Kadimela with Olvac Technologies, Inc., and we have an equipment, a roll-to-roll high-volume manufacturing equipment that can provide you, at the moment, we can even give you samples of 10 microns.
Okay, yeah.
Lithium on both sides of copper, copper being 8 microns thick. So that part is slowly being covered as far as commercializing the lithium metal anode for the lithium metal battery. My question
is that 8 microns on the copper foil or freestanding foil?
on the copper foil.
Okay, I was talking about
Yeah.
freestanding foils.
Oh,
So
you're talking about, okay.
Yeah.
Okay. So my question was actually about the artificial intelligence as far as it's being used to monitor things like the dendrite formations in lithium metal anodes. Do you have any information about that? Because I see even SES now is known as SES.ai, which
Yeah.
implies that they're somehow using AI in their safety features, in their battery management systems to increase safety in the use of the battery.
I know from a couple of companies that actually monitor or use models that are derived from monitoring batteries in usage, yeah, in order to predict potential failure modes. But I don't know, but that is not really related to solid state, but more in general. Companies like Accuray and others are doing that, or Twice, to name two. But I don't know what SES is doing with respect to that. They have AI in but I don't know.
Yeah.
Jeffert, I think you raised your hand.
Yes, I did. Yes, I did. Thanks so much. I was just wondering, since you have some market intelligence, I wanted to know from your perspective, do you see is there a commitment on the side of automobile manufacturers to switch to solid state battery technology, or is it just a competing technology that, is hoped to replace lithium ion and silicon anode batteries?
Yeah, I see it. I don't see a commitment for the sake of going to solid state. There are some applications and some at least one OEM that would have the need because of limited packaging space in this iconic model if he wants to get that get that pure electric. In order to have a certain range, you have to have a much higher energy density. For other OEMs or in general for the OEMs, I would say it's pretty easy. There are a couple of KPIs that have to be fulfilled, and at the end of the day, if it's more expensive, it gets tough. So cost is the biggest issue, and I know from the more advanced manufacturers of that is more in the meanwhile. I think I showed it at B, but meanwhile at A sample, they are still 20% higher in costs than normal lithium-ion batteries. They have a slightly higher energy density, but that higher cost figure actually prevents usage in the volume markets. So that is why I said, or why we said we do initially see the technology probably more in niche applications, where you really have a requirement for very high energy density, which is also true for some of the silicon players that focus, for example, on applications in aerospace or vertical takeoff and landing, where obviously every gram or every kilogram, every pound of weight matters double. So in those applications, price is typically also not as big an issue, or costs are not as big an issue. For those applications, companies are willing to pay double, 3, 4 times the price than what we see in automotive. But that would not fill up a gigafactory. That's the issue.
Thank you.
Michael.
Yeah, sorry, one more question. I'm still thinking dendrites, and in reality, rule of thumb for lithium is 1 milliamp per square centimeter current density. If you exceed this, there is high probability for dendrites growing. Obviously, if you have very, very low thickness of lithium, in this case, you can play with C rate. Just if it's very thin, then you can get very large number, but still 1 milliamp per centimeter square, and it is defined by exchange current density. This is term which is used in electrochemistry. I'm not sure that solid state electrolyte manufacturer can resolve this lithium. Look, my question is really, do you see any companies which have proof in their hands that they can exceed safely this 1 milliamp per square centimeter in the charge?
Not yet.
Yeah. All right. Thank you.
But I haven't seen everything. So
all right. What I'm saying is there is intrinsic barrier, probably. Okay.
Any more questions?
Hey, Wolf, this is Jason Masters. So if you were looking at the current commercial batteries that you have listed out here, which ones would you say are are best for stationary applications?
LFP. LFP technology is proven. Is typically you can achieve very long cycle lives. You can achieve very long cycle lives with NMC as well, but from a safety perspective, from a cost perspective, it's clearly LFP, and that's what we see. We expect that clearly to dominate, and even companies that used NMC in the past, like LG, I think they will go for that for stationary.
Do you think the energy density is going to be able to maybe double in the next 5 years?
For LFP?
Yeah.
No. That probably not, but you can do but what you can do is, and what's being done is actually with a very large with a very large format cells, you already achieve a higher energy density, and you can achieve a higher packaging size. So I think we are already at more than what we have seen in the last 2 years or so. I think we have seen a doubling of the energy density on the system level. Yeah, and there's probably still room, but I doubt that it's double. Something can be done, yeah, but
it's not critical because we are talking stationary.
yeah,
It actually is critical because floor loading weights are what
Okay.
we're solve urban environments.
Yeah, I see.
On a cell level, right now the LFP cell, it's already close to its theoretical energy density of LFP. It's close. There's a few percentage. So on cell level, we can't. But system level, yes, maybe, I don't know, system level, there's room.
Yeah, but I think a lot has been achieved. So it's very tough to really if you look at automotive applications, clear it's cell to pack and cell to chassis technology that's going to be introduced broadly. Yeah, China is 5 years ahead of Western companies despite Tesla, but all the others are behind. We do see first cell to pack coming to the market in automotive from Western OEMs in 2025. And then it takes still quite some time, but at the same time, it's already going in the cell to chassis direction that allows for further increase, and that's the main reason also for the increasing share of LFP in the total battery market, I would say.
Wolfgang, going back to your comment on LFP for stationary, just want to hear your perspective in terms of, say, sodium ion or other newer chemistries in that regard. Sodium ion, potassium ion, which offer maybe some potential cost and safety benefits. Any perspective?
Yeah, sodium ion. I mean, we have two. I think in the West we have 2 or 3 companies, and also going for specific high power applications in stationary. In general, I would say it can be an interesting alternative, but from our calculations, it only provides advantages from a cost perspective if we are if costs, as I said, if costs of lithium prices are above $20 per kilogram LCE equivalent, and currently we are, I think, at 15 or 14, 15, something like that, and that might go up to 20 until the end of the decade, but still with some question marks. The big advantage, I think, is with sodium ion, or maybe one of the biggest advantages is that you can transport the batteries or the cells completely discharged. That gives you that means you don't have all those requirements from a transportation perspective, from a logistics perspective. Disadvantage is the energy density, even in stationary. Jason just mentioned, for certain applications it matters, yeah, because it would mean you have and you it also matters because you have you simply have more containers, whatever, and that also adds to the cost side. The second point is the chemistries. Even in China, we do see various chemistry paths to be looked at. It's despite currently we have the layered oxides as the main route that are similar to ternary cathode materials, also from the manufacturing processes. That's probably the reason why they are used, because they were able to use the same suppliers. But a real cost advantage you only get by switching to Prussian white, Prussian blue, and that is still far away. Yeah. And also all the different Chinese players, they typically use again within the layered oxide different types of materials, and the supply chains are not there, not in China and not at all outside China. So we don't see a large share. We can think about a significant share in the higher one digit, or could have thought about a more significant share in the higher one digit range, 8 to 10%, if lithium prices were above the 25-30, as we have seen in 1.5 years.